So in the previous class, you remember we had started the discussion on compression members, and there were various types of buckling modes that we had discussed, and generally the Indian code handles the buckling issue of flexure, that is flexural mode of buckling, in quite a bit of detail, but it does not have enough, it does not provide you enough details for other modes of buckling such as flexural, torsional, etc. for different types of sections. However, for angles which are connected through only one leg, the code says that yeah, there you cannot avoid lateral torsional buckling, sorry, flexural torsional buckling you cannot avoid. Do not use the phrase flexural, lateral torsional buckling for columns. Okay, lateral torsional buckling applies only to beams. For columns, the similar phenomenon, it is known as flexural torsional buckling. I misspoke there. I meant to say flexural torsional buckling. So the failure mode of flexural torsional buckling of columns or compression members. So when there is an angle which is connected through only one leg, then the flexural torsional buckling becomes very significant, and then you need to incorporate or account for it. And there are equations given in the Indian code for that. Torsional buckling, there is no direct equation available, and flexural buckling, mostly even the situations where there is a possibility of flexural torsional buckling, the code recommends using the equations for flexural buckling primarily. I'll discuss all those. When we get into the design provisions, then we will talk about it. We are just developing the form work, the background, the foundation. So there were three important factors that I wanted to talk to you about. And until we discuss these in detail, it would be premature to get into the design provisions. So that's why I'm not getting into the design provisions yet. Okay. Residual stresses, who can tell me what you understand by residual stresses? Let me pick the name. This is a very simple question. So Indira, do you want to give it a try? What is residual
stress? Internal stresses, sir. Without any load being subjected, there are internal stresses within the member due to uneven due heating, hot roll process, welding, because of that.
Correct. So due to the fabrication or manufacturing process, which may be hot rolling or welding or cold forming, you may sometimes get some residual stresses logged into the member. Good answer, Indira. Thank you. So you may get some residual stresses logged inside the members, and that usually depends quite significantly on the member shapes and sizes and thickness of the plates and so on. So if you have an I section with very thin plates, you are not likely to have very high levels of residual stresses. But an I section with a very thick flanges, the flanges are of the order of 2 inches thickness, for example, 2 inches is 50 mm thick, okay, or above 100 mm thickness. So such kind of flanges will definitely have a very, very large level of residual stresses. Okay. So residual stresses do have an effect on the axial load capacity of compression members. Now, why don't they have it in tension members? Hopefully, we will discuss it a little bit today. If it is, my hope is that you should be able to understand after this discussion. If you are not able to understand, I can elaborate a little. So, good answer. The other factor was imperfections. So, imperfections, you understand, all of you understand, right? What kind of imperfections am I talking about? Is it the material imperfections that I'm talking about? Or impurities I'm talking about?
No, sir. Geometry.
Geometric imperfections.
Geometry.
Yes. So the geometry is not perfect for most of the. So when you buy such members from a supplier, you are likely to have some kind of an imperfection in the member. So as I was discussing, I mentioned, so if you have if you buy an I-beam, so if I buy an I-beam from, let's say, SAIL India or Tata Steel or somebody, and if I look very closely, what I will find is, so if I stand here at this end and I look in this direction, what I'll find is that over a long length, there will be some kind of a curve in these edges. These edges will not be perfectly straight. And in fact, the entire beam will be bent like that. Even though we are not applying any forces at that time, it is sitting idle. Even in that case, you will find that there will be some imperfections. Likewise, there can also be, so this is one type of a global imperfection. You may have global imperfection in the minor axis, like it is shown here. You may also have global imperfections in the major axis. That is, your web is bent. Okay, web is bent in its plane. So these are both global imperfections. Also, you may have something like a local imperfection. So again, if you look closely, you will find that there is a bit of a waviness in the flanges or in the web. Okay, so in the web, you may find that there is some kind of a waviness, and that is not very difficult to see. Okay, and you can actually measure that, and you can account for it. And there are some tolerances which are given in various Indian codes. So how much of this kind of a waviness you can have? What is the maximum limit on this out of straightness? Okay. So this can be called crookedness, out of straightness, imperfection. There are various words for this. Then there is a issue of local buckling. Now, local buckling is just like another buckling. Okay. Buckling is buckling, right? So local buckling will be governed by some other geometric parameters. Global buckling is governed by some other geometric parameters. So global buckling is generally governed by global geometric parameters. So I of the cross section will govern global buckling. Or torsional coefficient, torsional constant of the cross section will govern the global buckling, right? So Ix, Iy, J, warping, those things will govern the global buckling. What will be governing the local buckling behavior? Which parameters will be governing the local buckling behavior of a section?
Plate thickness.
Harish, right? What did you say? Can you repeat?
Plate thickness, sir.
Thickness versus
width.
Thickness versus width, yes. So thickness, so for example, if I have a flange like this, so the flange thickness versus the outstanding or unsupported length of the flange. So what is the unsupported length of the flange? Not in this direction. That is not the element property. That is not the governing number. What will be governing is this width of the flange. Similarly, for the web, the depth of the web. Okay. Now, of course, the boundary conditions also play a role. So a web of the, so for example, if I take the depth of the web, call it D, depth of the web D, divided by TW. So D divided by TW at a particular value, if let's say it is equal to a value X, and when it is equal to X, it buckles locally. Okay. So let's say we find that if D by TW is at a particular level, it buckles locally. But the same calculation can be done for the flange also. Now this will be, let's say, B. So B divided by TF. And that it will buckle locally when it is Y. So X and Y will not necessarily be same. Okay. There is no reason why X and Y should be same. And the reason for that is that the boundary conditions. So on a web edges, the two edges of the web are all restrained, right? And plus they are restrained against rotation also to some extent because of the flanges. So there is a higher level of restraint available for the web. And because of that reason, your X will typically be very, very high in comparison to Y. So X and Y correspond to the respective limits of width to thickness when the local buckling will occur, but also the boundary conditions play a role, and because of the boundary conditions, okay, due to boundary conditions, X will be much greater than Y. Fine. So okay, good. So now what happens is that I'm calling these three limit states, these three types of bucklings, as or three types of buckling and one type of squashing. That is also one type of a failure mode. So these four failure modes I'm talking about, but I am not talking about the local buckling as a failure mode. Okay, and there is a reason for that. I'll talk about that. Imperfections do govern the behavior, and residual stresses also govern the behavior. In fact, all three of them govern the behavior, and how do we account for them in the code we will discuss. Fine. This is just an explanation of various types of bucklings that we had discussed in the previous class. These things we had discussed in detail. Then we were at the residual stress effects towards the end. So we had talked about, before we went into the residual stress effect, we were talking about this idealistic kind of a theoretical curve, which accounts for two types of buckling mode, or two types of failure modes. One is the plastic yielding failure mode, and that goes up to lambda is equal to 1. And at lambda is equal to 1, the two curves, this one and this curve, here they meet, which basically means for any value of lambda greater than 1, you are going to have a plastic buckling. This sounds interesting, but when we derive the expressions or when we derive this equation or this design requirement or design calculation, there are several assumptions we are making. We did not account for the residual stresses. We are saying that the entire cross section is yielding exactly at a particular point. So up till that point, until we start increasing the stresses, and up to this level of stress also, nothing has yielded, and suddenly everything has yielded. So we go from 0.99999 FC by Fy, nothing has yielded. And exactly at 1, the entire cross section has yielded. So there is an assumption here, because if the residual stresses were present, this would not happen. This will be more gradual process. That is one assumption we have made. Another assumption that we have made is that this equation, which is pi square EI by L square, this is that equation. Pi square E, you can take R and break into I by A, you will get pi square EI by L square. Or here, pi square by EI by L square. So that pi square EI by L square assumption is true only for a perfectly straight column. If the column has a finite amount of, even though small, finite amount of imperfection, the critical axial load capacity of the column will be lower than this, and that will start to play a role. So you will not exactly meet at this curve, and you will be somewhere below this curve. Okay. Then the two factors will interact, and that interaction also has some role to play. So we will talk about how the residual stresses may affect the column capacity in this slide, in the subsequent slides. So as we were talking in the previous class, if you had a coupon, let's say compression coupon, it's a small cube cut from, so if I cut a small cube from somewhere here and test it under compression, we are expected to see this kind of a stress strain plot. Okay, but if I don't test that cube, but test the entire section itself, I will be getting a plot which is not a bilinear plot, but it's a curvilinear plot like this, right? Can somebody quickly explain to me why would the stress versus strain plot for the stub column section not be this one, but this one, whereas it was this one, it was bilinear for a small portion that was cut from that same column? Maybe I'll give you Leo. Can you explain?
Yes, sir. Hello, sir.
Yeah.
Sir, when we load as step column and like coupon test in the step column, when the point reaches to A, the sum of the fibers will yield, and the other fibers will not be yield. And in progressive loading, the yielding of fibers will be increases. At particular point, the all fibers will be lead. But in coupon test, the yielding of every fibers will be equally. It will be done equal manner. So at particular stage, all
Okay.
fibers will be yielded completely, and the plastic zone will be entered. But in other state, it is gradually some fibers are yielding, and that yielded fibers will be
Leo.
so
So Leo, wait.
okay.
So I'm not sure what you're saying. So most of it I understood. One part where, like in a section, let's say you take a column section like I section, like here. Why would not all fibers start yielding together? Why should some fibers yield and some fibers not yield? Leo, can you explain again?
Hello, sir.
Yeah, the question is, you're saying that in case of a coupon, all the fibers start yielding together, but in case of a column, only a few fibers start yielding first, and then
Sorry,
some other columns.
due to the residual stress.
Yeah. Good, fine. So that's the correct answer. So basically, you already have some stresses. So if to start with, the net total stress in the cross section is 0. Okay. However, that is the average stress. However, if you look at individual locations, you will see that they have some stresses, but they are just distributed in such a way that so that the net stress is 0 or average stress is 0. Right? So now what will happen is that as you push this cross section into compression, the average stress will be changing in proportion to the external load. But individual fibers, if you see, some of them were in a higher tension, they will be coming into lower tension, and some of them will be approaching very quickly to the Fy value. Okay, so some of these fibers will be closer to Fy than some other fibers. So these fibers are closer to Fy in compression than these fibers, and as a result, some of them will reach the yield point first, then the other fibers, and at that time, as soon as they reach the yield point, they will stop contributing towards the elastic modulus of the section, average elastic modulus of the section. So let's say I keep pushing them in compression. As soon as we reach this point, the net AE value of the cross section will be reduced. Only in this particular case, only this much of the cross section area is contributing towards AE. In this case, only this much of the cross section area, is contributing towards AE. And in this case, none of the cross section area is contributing towards AE. The entire cross section has yielded. Okay. Fine. So as a result, when I do a compressive test on this stub column, the curve deviates from the biaxial behavior to this kind of a curvilinear behavior. But after a certain amount of strain, definitely the entire cross section will be yielded, and then you have the same capacity as it would have been in case of a coupon. Same sigma y will be achieved, but it's just achieved a bit gradually after a certain amount of strain. Okay. So overall force that this stub column will resist is not different from the overall force or the stress at which it will yield versus the stress when the whole thing yields here. The two stresses will be same, but this will undergo much larger deformation before this yields, and this one will undergo less deformation before it yields. Okay? And that is because of the residual stress effect. Now, see, for a step column, it sounds okay. So residual stress doesn't seem to have any role to play. I mean, residual stress only what it did was introducing, or it was increasing the amount of strain it takes for it to yield fully. But ultimately, the yield stress is the same, or average yield stress that you achieve, maximum stress that it can carry is the same as this one. So what did it change? What did the residual stress change? So if it were a tension member, for example, and you apply a tension, again, you can expect similar kind of a behavior. Okay, you would have this, on a coupon, you will get this behavior, but if you take a step column like this and apply tension, you will get this kind of a behavior. Okay. So there we said, okay, nothing changed. But for a column, we cannot say that nothing changed. Something has changed. What has changed is that in that process, so let's say we deviated from A. A was up to A, it was all hunky-dory, all perfect, all perfectly elastic. We deviated away from A. Now we are here. At that point, definitely some of the fibers have yielded. That's why we have deviated, right? So some of the fibers are not contributing towards the axial stiffness, which basically means that the net E has changed. And for buckling, what is the equation? Euler's buckling equation? It is pi square EI.
EI by L square.
So this EI, it is assuming when it is putting this EI value that E is uniform to the cross section. Then you can use the EI value. But if EI is not uniform, so you have a column like this, you are applying pure compression on this. Pure compression. Okay. You're applying like this. And what you're finding is that some corners of this cross section have started yielding already. If they have yielded, then the contribution from these fibers towards E is 0. Correct? And as a result, your net EI becomes less. And that should have a role to play in how much capacity it can, at what load it will buckle. So your buckling capacity is reduced. Right? So there is a nice theorem called theory of tangent modulus. It was proposed in 1889. Okay, and what this gentleman Ingersoll he suggested was very, I would say, elegant. So what he suggested was, now listen to me carefully. We have been talking about two modes of failure, right? Primarily, ignore all of the torsional buckling and so on. Primarily two modes of failure: squashing and flexural buckling. Fine? Agreed? Two primary modes of failure of a column: squashing or crushing, and the other one is flexural buckling. Now, what he said was that actually the squashing mode is not very different from flexural buckling. All that is happening is that as you keep pushing it closer to the yield point, some of the fibers start yielding early, and then your elastic modulus reduces. Okay, and for that kind of a cross section for which the net E or net EI value has reduced, for that section, if you calculate the buckling load, that will give you the column capacity, and it will even predict the buckling, the squashing capacity. Okay, which makes sense, right? Going back to the previous slide, here you started applying load. As you keep increasing the stress, average stress is less than sigma y. Almost the entire cross section has yielded, but only some parts are not yielded. As soon as the entire cross section yielded, you reach the sigma y value. Average stress is sigma y. The entire cross section has yielded. What is the net buckling strength of this column? What will be the Euler buckling strength of this column? The entire cross section has yielded only
0.
0, right? Because pi square EI by L square. Yes, good. So E is 0. So EI will be 0, and therefore you have 0 strength available, right? So just before yielding point, you had reached the capacity, right? So that makes a lot of sense. So what he suggested was that instead of counting for squashing mode of failure separately and buckling mode of failure separately, it's all the same buckling mode of failure. Only thing is that in the buckling in the equation for buckling mode of failure, you have pi square EI by L square. Instead of using EI, that is elastic EI, don't use elastic EI, use EI tangential. Okay, and what does he mean by EI tangential? That is, as you keep increasing the P value on the column, your effective E will keep changing. So at any given load, whatever the effective E or effective EI is, use that one. I'll show you a quick calculation or how to derive it. So let's say I have a column like this. Okay, you can see this column, and I'm talking about flexural buckling about y-axis. That is the weak axis. Correct? Y-axis is the weak axis, and this column is likely to buckle about y-axis. Now, of course, we know that there are residual stresses. Now, and some of the fibers will start reaching the yield point sooner because of the residual stresses. Now, what this theorem says, the theorem of tangential modulus. The theorem of tangent modulus. What it says is that, let's say you have a fiber in this column cross section here, and another fiber would be here, and they would be in the under same stress as long as you are talking about buckling about axis y. So both of them will be in the same situation. We are looking only at this fiber, only at this fiber. Okay. So let's say the fiber has this dimension, I call it di, this dimension I'll call it bi, and the fiber is numbered as I. Likewise, there are hundreds of fibers in the entire cross section. Okay, so the fiber is numbered as I, and the distance of the fiber centroid from the neutral axis is xi. Okay, so the total, I want to calculate total EI of the cross section, right? In order to use that theorem. So for the calculation of total EI, what do I have to do? I have to first calculate the EI contribution coming from this particular fiber. So for that, first I'll calculate the I contribution from this particular fiber about y-axis. So I, that is moment of inertia, area moment of inertia, for the ith fiber about y-axis. So there will be two components. One component is the area of the fiber, that is bi di multiplied by xi square. That is bi di multiplied by xi square. Okay. Plus, if you want to be very accurate, you can also take, depending on how fine your meshing is. If your fibers are very, very tiny, you can you need not do this second component. This second component of I will be 1/12 of a bi di cube, right? So we are talking about bending about this axis, right? So that is its local moment of inertia. So local moment of inertia about the centroid, that will be 1/12 bi di cube plus this, that is from the centroid of this one to the neutral axis. Okay. And the corresponding EI contribution from this particular fiber, EI will be equal to the E for the local fiber I multiplied by this I value, right? Multiplied by this I value. Simply this I value is going in there. Now, if the fiber at a particular point, and if we let's say keep increasing the strain in the cross section, so as the strain in the cross section keeps increasing, some of the fibers will start going under yielding. So if the fiber I has yielded, that is, if it yields, then you take EI is equal to 0. If it has not yielded, then you take EI as whatever the original EI was. So in this case, it could be 210 power 3 MPa, 200 GPa or something. Okay. So as soon as your EI becomes 0, these fibers will not contribute towards EI. So your total EI of the cross section will be equal to sigma of all individual fiber EIs. And as soon as one fiber yields, its E becomes 0, and then you stop incorporating or stop counting the contribution coming from that particular fiber, and the rest of the fibers will be counted still. Right? So this is the catch. So now what you do is you use this EI total, which is So now we use this EI total, and the column capacity will be P critical is equal to pi square EI total by L square. Fine. So pi square EI by L square. But now this EI is actually given by this, wherein this E value has to be the pre-yield or post-yield value, depending on what situation that particular fiber is in. Okay. Is that part clear to everyone? So here in this particular expression, I have not taken into account the secondary component of the moment of inertia. I have already only accounted for E multiplied by area multiplied by R square. That was the primary component. So bi di corresponds to area multiplied by x square. So that is area multiplied by R square is E multiplied by area by R square is incorporated in that equation. If you want, you can incorporate the second component also. Okay. Is that okay? Is that clear?
Yes, sir.
Yes, sir.
Good. So now I have given you one assignment. It is there in the class notes also, but the class notes assignment I have made a small modification. I've changed the cross section from ISMB, and I have asked you to do it for both minor axis and major axis. Okay. For you to follow the difference between the two. Sorry. Okay. So this is the question I have given you. So you have to take one ISWPB section. Such sections definitions are available in IS 808, I believe. No, 808 is not in the parallel flange section. IS code. I have in my first lecture notes. You can find the IS code that has the definitions of parallel flange sections. You go there. It is a wide flange parallel flange section. 200 by 74.1. 4.01 section. Is it 74.1 or 0.1? 0.01, 74.01. So look at the properties of that section, and then you divide that cross section into number of grid points. And you don't have to do it throughout at once. First, you can define the grid points in x direction, then you can define the grid points in y direction. And then there is a procedure that I have given here. So first, you have to divide the cross section into a grid. Then assign the residual stresses in each fiber. Assume the uniform applied strain in the column cross section. Start with a small value and increase in each step. And as you go ahead, as you keep increasing the strain, you try to calculate the EI value corresponding to that strain. That is net EI, total EI. And then also calculate for the strains, you would know the stress in each fiber and add all of those stresses with the area, multiplying with the area. You'll get the total force in the cross section. So once you match that force with the pi square EI by L square and get the corresponding length. So what you need to do is you change the strain value. Increase the average strain. Okay. So as you increase the average strain, or mechanical strain, you can call it, average additional external strain that you increase. So as you increase, start from zero. Initially, everything is zero. Zero strain is there. Then you start increasing to, let's say, epsilon 1. As epsilon 1 increases, for epsilon 1, you calculate the total strain in each fiber. Okay. So each fiber had a particular level of strain value, right? Because you were already at some kind of stress. So this was already Fy by 3. That is corresponding to sigma epsilon y by 3. So for this particular fiber, if let's say this is in compression, right? So this was already in compression, and now I have increased this by epsilon 1. So the new strain will be this much. Okay. So from epsilon 1, calculate the total strain in each fiber. Then calculate the E value of the fiber. Calculate the sigma EI for the cross section. Calculate pi square EI by L square. Okay. Then also from this strain, another branch is going in this direction, let's say. From each strain, you calculate sigma value in each fiber. Okay. From that sigma, you calculate sigma multiplied by A, that is Fi, in each fiber. From there, you calculate, that is P. Okay, this P is the external load that corresponds to this particular strain, and this pi square EI by L square is the load that will make it fail. But now you don't know the L value. So what you need to do is balance P is equal to pi square EI by L square. And from there, calculate L. Okay. Then what it means is that the column capacity basically is, if you want to plot, what you can do is you can plot. Initially, your strain was 0, and suddenly you increase the strain to a certain level, and what you will get is L here, and your P that you got somewhere here. Okay. Subsequently, you increase the strain value. As you increase the strain value here, yeah. So as you increase the strain value here, your L will reduce and P will increase, and you keep going this way, and you will get some kind of a behavior. Okay. And it's important that you create this mesh fine enough, and also you go in smaller intervals. So these intervals should also be very small. So you go in, let's say you should have at least something like 20 to 30 data points from your smallest EI, epsilon 1, from your smallest epsilon 1 to the final value. You should have at least 20 to 30 data points or more. And also you should do fine enough meshing. Likewise, you need to develop the curve for minor axis bending. That is, when you calculate the sigma EI value, whether you consider IX or IY, that will play a role. Okay, and IX, for that you have to calculate RX multiplied by A, RX square multiplied by A. okay, versus or depending on which neutral axis you are talking about. Right? So that's what you need to do, and you need to calculate the capacity of the capacity curve. So basically what you will get at the end is a column capacity curve. So KL by R divided, plotted against the load or the capacity. Is that clear to everyone? No? I'm not hearing any yes or no. Anyway, this is an interesting exercise which tells you how the code had evolved, and that's why this is one of the assignments. This may be slightly, if you have no experience with programming of any kind or any Excel sheets work you have not done, it might be slightly involving. I would encourage you to use MATLAB, or otherwise you can do it in Excel also. Okay. If you need more time, you let me know. I can give more time. This may be a slightly involved problem to work with. So all the instructions are given, all the hints and everything, what steps to be followed have been given here. So, okay,
Hello,
please
sir.
do try. Yes.
Yes, sir. Can you explain the step one, so how to divide the cross section into grid?
Yeah, so that is up to you. I would rather like if some students can give it a try
Yes,
rather
sir.
than.
I don't know any MATLAB or how to do it.
Okay. See
So I am.
if you don't know any MATLAB, Excel you should know at least, right?
Yes, sir. Some
Right.
basic things I know, but
You only need the basics. So let's say the dimensions of the cross section, the dimensions of the total beam are known to you. This is the beam. The
yes, sir.
overall dimensions are known to you, right? So let's say you decide that I want to divide I'm calculating the EI, or I'm calculating this curve,
Yes, sir.
lambda versus capacity, be critical, for the minor axis. Likewise, there will be curve for major axis. Okay, so this one will be minor axis. This is how it should look like. And this will be my major axis. Actually, this has been developed for one particular type of a cross section and particular type of stress distribution here. What you see here, this is how your curve should come out. There is elastic buckling part and there is a residual stress. So basically, this is where the quashing happens, but in the influence of residual stresses. If the residual stresses were not there, you would get this behavior, this broken line. But because of residual stresses, you have this kind of a drop. So you should be able to match your data with this. Typically,
Okay, sir.
with major axis, minor axis, you should get this behavior. Major axis, you should get this kind of a behavior. Okay.
Okay, sir.
So let's say I'm worried about minor axis for now. So I'm looking at the minor axis behavior. For the minor axis behavior, I need to know that I know that I have to create partitions in this direction. Like my fibers have to be distributed this way. Similarly, in the web also, right? Because I have to count the distance from the neutral axis, and neutral axis is this one, y axis. So I need to know the distance of each fiber from the neutral axis. There is no advantage in cutting the fibers this way, like one fiber here and one fiber here. I could just account for both of them together as a single fiber. That makes sense. But here, the contribution of this fiber will be very different from the contribution from this fiber. So I should not do that. Also, in the web, it is important because the residual stresses are varying. So you may have to, the residual stresses are varying, right, in the web also. So then it makes sense to actually divide the web also into finer parts so that individual stresses can be accounted for. Fine. So you take fibers, you divide them into a separate number of parts, and in an Excel file, you can make a kind of a separate rows. First row for first element, let's say this element. Then second row for this element, third row for this element. Then you can keep listing its location. The location means its x coordinate, y coordinate value, that is centroid of this x coordinate, y coordinate, and those things you can calculate, and you can feed formula for calculation of x and y. Okay. Likewise, it's di, etc. And once you get that, also from the strain value, the amount of strain that you're applying from there, how much is the So then you do strain value, strain 1. Strain, from strain you calculate sigma 1, also you calculate E1. And then from there you can calculate the length. So then you can slowly increase the strain value to strain 2. You get another set of length 2. Okay, this length will not be for individual fiber, of course. This length will be a combined one. That will happen after the integration of this thing. You will get the pi square EI by L square. And after integrating this sigma, you will get summation of sigma times AI. Okay, and then you equate the two and you get L value. That L value will be corresponding to this particular epsilon bar. This is one set.
Okay, sir.
This will give you one data point on this. Okay, you try it. If you are having difficulty, we can explain further later.
Okay, sir.
Okay, so actually, this is how the behavior should look like. You try it, you should get this kind of a curve, perfect elastic buckling, and then this one. So here we have already only accounted for the residual stress effects. And residual stresses also we have assumed them to be linear, but in reality they will never be linear, right? They will always be either this or something like that, and that will change the shape of this function. So it may be sometimes slightly like this, sometimes it may go slightly like this. So it may not exactly be a straight line. It is turning out to be a straight line because we assume that the residual stress is to varying as a straight line. Okay. Then comes the next effect, that is called imperfection effect. But I don't want to get into that section today. We'll consider that we'll discuss this second effect, imperfection effect, in the next class. Okay. So any questions about the residual stress effects and the theorem of, or the theory of tangent modulus?
Excuse me, sir.
Yeah.
So
Sure.
how is this theory of tangent modulus accounting for stocky columns?
Yes. So see, the thing is, stocky columns, if it is very, very stocky column, it does not as we expected. And for a very stocky column, the capacity is same as if there were no residual stresses. But as the column starts to gain certain length, okay, the column capacity will start to decline because of the residual stresses. Most of the you are slightly away. At this point, you think that Py is the yield stress. Okay, this was the yield stress value. You can see the mouse, right?
Yes, sir. Yes, sir.
So let's say stocky column is somewhere in this domain up to this range. KL by R of up to 40, you can say stocky columns are there. So for stocky columns also, you can see that there is a decline in the capacity of the column because of residual stresses. Now, idea was that stocky columns should only fail in yielding, and as long as yield capacity did not change, the stocky columns should not lose their strength. But what happens is that stocky columns, even though these are actually undergoing some level of some kind of inelastic buckling. So after most of the cross section has yielded, only the middle portion would be remaining, which was earlier under very high tension. So that portion would be under some kind of will not have yielded yet, but by that time the cross section net EI would have reduced so much that it will fail under buckling. So even though the cross section has not completely yielded, it will fail under buckling, and that's why even for stocky columns you see a change in the capacity. In fact, for very slender columns, it does not have much role to play. That behavior is governed by imperfections. So when you have columns with imperfections, then the behavior will significantly change from this nice exponential curve, 1 by L square curve, hyperbolic curve rather. Okay, I hope I answered your question.
Yes, sir. Yes, sir. Thank you, sir.
Anything else? No? Okay, so if there are no more questions, I'll call off this call it a day. Okay. You can always shoot me a question if you have any. You can write an email, or otherwise you can ask questions in the next class.